We're going to come back now. We're switching gears into the solid state. Our next speaker is Dr. Andy Mounce, from Sandia National Laboratories. He's the one who has the NV magnetometer in the back corner there, which we'll also spend this afternoon doing some fun stuff with. He is also big into turtle husbandry, which I feel the need to mention. I think that should be celebrated. Yeah, take it away with the second session of the day. Thank you.
So now that we've discussed turtle husbandry, I've got to give the background. Apparently in Albuquerque, one of the things that people do is they just have box turtles living in their backyard. And when we bought my house, I went out one day after it rained, and I looked one way, there's a turtle. I looked the other, there's another turtle. Turned out we had about 6 adults, and then they just babies popping up everywhere that spring. So anyway, that's one interesting fact you get about me. So anyway, thanks for inviting me to this workshop. My name's Andy Mounce. I'm at Sandia National Laboratories, a specific subset of the Center for Integrated Nanotechnologies, and I'll discuss that, what that means here in a little bit. And I'm going to talk about a focus of quantum sensing with diamonds, and specifically the nitrogen vacancy defect in diamond. So a little bit about me, so I'll just give some background, though, how I got to this place. So I actually started out at a small liberal arts college doing physics, Eastern Illinois University. Stayed for next year, got a master's in mathematics. Then I went to Northwestern University, where I studied high-temperature superconductors with traditional nuclear magnetic resonance, so inductively detected. And I was a postdoc at Los Alamos after that, also doing solid-state NMR. And that was fun, too, because we got to actually look at materials that had plutonium and uranium. So I actually was designing ways to actually study plutonium with NMR. All right, so then I actually went to Sandia National Laboratory and somewhat switched gears, though I find the relationship between NMR and quantum computation an easy step, because a lot of the sequencing that you do to do NMR studies, the pulse sequencing, is very relevant to quantum computation. So what I liked about that was that I got a transition from, it seemed like a big step at the time, but then it wasn't so big in the long run. So then after being at Sandia for about 4 years, I got the opportunity to start at the Center for Integrated Nanotechnology, where we're a user science center. And what we were pushing towards at that time, I got to start a program for quantum sensing with quantum defects, and an overall program with what I called quantum defects. And that really then became to me like a hybrid of the what I did as a graduate student and postdoc, and then early in staff, which is, I think, the right track for what I would recommend students do, is try to change a little bit and then combine them later. So a little bit about where I work. So I work at a DOE-funded nanoscience center. So we are one of 5. So there's one at Berkeley, Oak Ridge, Argonne, and out at Brookhaven. And these nanoscience centers are like you can almost consider us like a neutron scattering facility, but instead of neutrons, we just do nanoscience. So anything that's related to small scales. And so this is centered around actually users, so people that write proposals to come work with us, and we do a variety of different things at the nanoscale. We have 4 different thrusts: quantum material systems, which is what I'm part of. We have nanophotonics, which I am an interloper in. And then we have in situ characterization and nanomechanics, a lot of TEM type capabilities. And then nanoscale soft bio and composite materials. So each of these 4 thrusts is what we focus on. One of the things that we are actually known from the Department of Energy Office of Science is actually really good with microelectronics and quantum, is some of our, and some of the key capabilities that we have that are relevant to quantum information sciences, not just defects in diamond. We have a Class 1000 clean room with e-beam lithography, photolithography, all the etching tools you need so people make devices, quantum devices there. We have an ion beam laboratory that will, we implant ions, both shallow, deep, variety of ranges. In my laboratory, we have a lot of room temperature and cryogenic optics, and a lot of focus that I have as well as instrumentation and software. Okay, so that's kind of an overview about a bit of history of where I come from and where I'm at now. I'm going to do introduce the nitrogen vacancies from, you guys have already been here listening about quantum sensing, but at least I'm going to give my definition of it that I like to use because it's relevant to me. And we'll talk about these quantum defects. So a defect in a solid state material that you can use for quantum application. And today we're focusing on sensing. And the specific defect we're going to focus on is the nitrogen vacancy in diamond. So I'll introduce the physics of nitrogen vacancies in diamond, how they actually work as a quantum system. Now, one of the nice things about nitrogen vacancy is there's a lot of different sensing modalities. You can go from a single nitrogen vacancy in a material or to ensembles. You can place a material on a diamond. You can put the diamond on top of material. Or even integrate it in a high-pressure diamond anvil cell, for example. We can go from high temperature. You can actually heat them up to hundreds of degrees, or even go down to dilution temperatures. All right, so the modalities of nitrogen vacancy sensing are varied enough that there's a lot of different things you can do with them. All right, so then after a good chunk of introduction in this area, we'll talk about actual quantum sensing with nitrogen vacancies in diamond. And I've got a lot of examples both from what my group is doing and some of our users, as well as within the diamond community as well. And I'll split this up into two different categories where we're actually measuring static magnetic fields, so DC, and then AC magnetic fields. So it's another benefit of the nitrogen vacancy in diamond. So not only can you do a variety of singles, ensembles, all kinds of environments, you can also sense anywhere from DC up to gigahertz in magnetic fields, depending on the sensing modality and different quantum control configurations. Okay, so while this is a block of text, this is one that I actually like. I think had some of this at QCamp, and the students wrote it down. It was amazing. They liked the list. So I stole this from Review Modern Physics, the definition of quantum sensing. And the thing that I like about this is a bit, we actually sometimes have issues with using ensembles of NVs considering it as a quantum sensor, and some of our referees reports from journals. But the definition is of quantum sensing is describes the use of a quantum system, quantum properties or quantum phenomenon to perform a measurement of a physical quantity. And so there's kind of three tiers of this. There is, all right, you're just using a quantum object. All right, so in our case, with NV ensembles, that's probably one of the biggest ones. You're just using the spin states of an NV to detect a magnetic field, for example. Another version is using quantum coherence, which is slightly higher complexity. This is actually used with kind of magnetic noise and some of the AC type sensing. And then actually using quantum entanglement to improve sensitivity. And actually for NVs, that's kind of more of an up-and-coming field, but not as much the immediate utility. All right, so so with NVs, we're kind of focusing in these two areas, 1 and 2. And then the definition of a quantum sensor, there are some key properties kind of also listed here. Has discrete energy levels, so 2-level system or even ensembles of 2-level systems. You can initialize into a well-known quantum state. You can coherently manipulate that state. And then finally, it interacts with some physical quantity, such as electric field or magnetic field, which shifts the energy levels or relaxes between them to be measured. So this is kind of the overview definition of how we describe quantum sensors. Okay, so I'll tell you that the nitrogen vacancy is considered a quantum sensor, and I call it, it's actually part of a category of that I call quantum defects. So a quantum defect, oh yeah, we got more text and definitions. It's all right, bear with me. A quantum defect is what I call lattice vacancy, atomic substitution, or combination of those, which can emit single photons and have ideal properties for sensing or communication, or even computation. I left that part out, but it's, I would say, not as, as dominant in the quantum computation field. So examples that, that we work with in my laboratory is the nitrogen vacancy in diamonds. So this is a diamond lattice, and we have one nitrogen next to a vacancy in the crystal lattice. And it has a 2-electron spin state that you can control. Another defect that we've been using recently is the boron vacancy. So this is just the absence of a boron in hexagonal boronitride, which is a 2D material that you can exfoliate. So one might imagine how that could be useful as compared to a bulk diamond. And another example, which is a G center in silicon. So in this case, a G center is a carbon with some silicon damage that actually gives you single photons coming out of silicon. And the reason that we pursue this kind of research is actually more from the quantum communication side. You can actually integrate these kinds of defects with silicon photonics, and now you have a single photon generator within silicon photonics to actually perform quantum operations and communicate over long distance. So the nice thing about quantum defects, and it has 3 key properties that actually make it quite an effective total quantum system. So they kind of act like artificial atoms in some state, or an atomic system, where it emits photons. So it has energy levels that you can excite, and it will decay to release a photon, which can operate like a communication qubit. They often, they have electron spins, which gives you kind of quantum processing type capabilities, and a lot of them have access to nuclear spins, which act like a spin memory. So it's kind of an all-encompassing quantum resource that's actually embedded in the solid state. Now, in some cases, particularly with HBN and diamond, you can operate at room temperature. That's not true for all defects. Nitrogen vacancy and boron vacancy are actually ones that do operate at room temperature. Others, like the G center, for example, in silicon, well, that's a narrower band gap material, silicon, so thermal excitation require you to get down to 4 Kelvin. But the nice thing about particularly silicon and diamond is actually carbonate 12 and silicon 28 enrichment. So you can make nuclear spin-free environments and get really long coherence time. One of the detriments of HBN is actually you can't do that. Boron and nitrogen don't have spin-free isotopes, but we're learning to deal with that anyway. All right, so let's talk a little bit more specifically about the nitrogen vacancy in diamond. So this is in general, even without isotopic enrichment, carbon, which is the only constituent of diamond, only has 1% carbon-13 natural abundance. And we actually work with groups that do isotopic enrichment with CVD growth on top of the diamond, so you can get very low carbon content and very long coherence times. You have the access to optical readout initialization, so that can be optically controlled, which all of this gives you nanoscale magnetic resolution and sensitivity. And we'll talk about where this fits into the magnetic sensitivity scale. Quantum sensors like Peter uses, they're much more highly sensitive, but they don't have the same spatial resolution. All right, so you get a trade-off in these sensors that you have lower sensitivity, but still rather decent, but you get nanoscale resolution for magnetometry, and a wide range of temperatures and operations. Now the challenges, though, I can tell you all the nice things and hide these, but the challenges with this, and also makes it fun, is that for example, the sample must be nanometers to microns away from nitrogen vacancy defects to actually do a measurement, because magnetic fields die off radially. It's ideal to have them as close as possible. The nitrogen vacancy activation in diamond is actually dependent on depth, and very low to the surface. So for some applications, that's that's a problem. There's actually multiple charge states that you have to stabilize, and there's kind of charge state engineering that we do to make sure that it's the NV minus. As compared to other quantum defects for quantum information, has a long shelf life, meaning that it takes a while to decay back to the ground state, so you don't have a lot of entanglement photons coming out. And then finally, there's actually challenging to place NVs accurately with confidence. A lot of the, an activation process in solid state is usually stochastic. You have a probability of, a nitrogen pairing with a vacancy and actually being a useful defect. So there's in the bulk, even if you have one nitrogen placed in the material, there's only a 30% chance that it's going to activate, for example. And that gets much worse close to the surface. All right, now, so that's kind of the overview of nitrogen vacancies in diamond. I'm going to talk about, kind of the physics of this going from, the different quantum levels that are accessible to us and how it relates to, for example, atomic physics. So, on the top, I have, pictures of an atom with its orbitals, right? And this is for electrons with typical atomic orbitals. And the bottom, since we're in the solid state, now we're talking about, particularly in a semiconductor, that we're talking about instead of, sp and d orbitals, we have, valence bands and conduction bands. And diamond, in particular, is a very wide band gap semiconductor. So it's a 5.5 eV band gap. Meaning that you can actually have electronic states, two electronic states within the band gap, so a ground state and excited state. So one might imagine thinking of that as like an s orbital versus a p orbital. So you can make transitions going from the ground state to an excited state, just like an atom. And of course, since it's quantum, you can't just go to an arbitrary location within that band gap. Now, you can photoexcite these defects, just like you can in an atom. So you can, if you apply the proper wavelength in an atom, you can excite from one level to another, and then it will actually emit a photon, right? And for example, you can have a hydrogen atom. This is kind of displayed by the absorption spectrum. So you can do the same thing with these quantum defects. You can photoexcite them, and they will emit photons. But it gets a bit more complicated because you're in the solid state and you have phonons everywhere, so quantized lattice vibrations. And so in that case, instead of having these sharp emission lines like hydrogen, well, you only have one what we call zero phonon line, right, and a huge phonon sideband, particularly for the NV. So this is the direct energy levels here, and all of this are quantized phonons. So you can actually emit lower energy photons because you're also emitting a phonon at the same time. And I'll show you a picture of that here in a second. But the pictures I have here from the atomic scale you can find in also a very nice book. This was from Quantum Physics for Babies, and you can find more information there. Perhaps we should make quantum sensors for babies now after this. Okay, so with a little bit more detail about the solid state, I had shown a very simple picture where you can excite from a ground state to an excited state and then release a photon. Well, that's actually a bit more complicated here. The levels that I showed are this 637 nanometer zero phonon line. And in both the ground and excited state, you have these extra phonon levels as well. So you can actually absorb non-resonant light, so higher energy photons, and then even emit lower energy phonons. So this diagram here is the absorption in red, all right, and then the black is the emission spectrum. All right, so this is actually a benefit too. So now you can actually divide your absorption and emission. You don't have to resonantly pump and be very accurate. You can actually kind of, throw a bunch of junk light at it and still get optical excitations. And the nice thing about that too is something you can actually see. So one of the demonstrations that we'll do, and I've got a nice picture from where we did it at Children's Museum, is that I have a little demo with a diamond that's full of NVs. You can pump it with a green laser wear some optical glasses to screen out the green, and you can see a very bright red glow from these diamonds. Okay, so the thing I liked about this is that it's an actual observable effect with your eye in a very simple experimental setup, and we'll take a look at that later. Okay, so we've talked about the orbital degrees of freedom. The next, and that is what gives you the light. The next level of quantum numbers accessible are the spin. And so, the spin is a mystical quantity. The electron spin explained. Imagine that it's ball and it's rotating, except it's not a ball and it's not rotating. Don't ask me anymore. So, of course, we know that a spin is intrinsic angular momentum, which is carried by elementary particles. And the total spin of electron is defined by a spin 1/2, and it gives two possible quantum states. So you have plus 1/2, minus 1/2, and the energy of that is the Zeeman Hamiltonian. It's relatively simple. You have a G factor, Bohr magneton over 2, and then you have the dot product of the applied magnetic field. I call this B0 from the magnetic resonance standpoint because it's typically the larger one. That's your bias field, and then the dot product with your spin state. So if you look at the energy, and I put this in gigahertz, E over h bar, as a function of magnetic field out to 1,000 Gauss, you get spin 1/2 getting lower energy and plus 1/2 getting higher, and you can have a resonance here that depends on magnetic field. All right, this is your magnetic resonance, and that difference in energy as a function of magnetic field just gives you a nice straight line, which is about 28 gigahertz per Tesla for a standard G equals 2 electron, which is pretty relevant for electrons in diamond. All right, so 28 gigahertz per Tesla. But the NV is actually more complicated than that. So it's not just a spin 1/2 state. You may recall I told you it's a spin 1 state. So that's a fun little extra quantum mechanics added to that. So you can have, when you have total spin as 1, you can actually have 3 different spin values. You can have up, up, down, down, up, down, and down, up. And you can subdivide these into the wave function symmetry to get triplets and singlets. And so the ground state of the NV is actually a triplet state. Okay, so you have an accessible 1, 0, and -1 electron state. Now the energy levels are now defined by this Hamiltonian. So you still have the Zeeman interaction, but you also have this dipolar type interaction, D, which gives you a zero field splitting, actually, depending on the spin state. Okay, so if D is 0, the energy levels are pretty simple. For spin 1, you have increasing energy 0. You have 0 Zeeman interaction, and -1, you have reducing energy. Okay. Now you have actually 2 sets of magnetic resonance, though. So if we look, if we add a D parameter, all right, which is this dipole interaction, and the NV is particular 2.87 gigahertz. All right, so this is what we call the zero field splitting. That actually increases the energy at 0 magnetic field for the plus or minus 1, still degenerate for plus or minus 1 at 0 field to this 2.87 gigahertz. And now you have actually 2 transitions, resonances, from -1 to 0 and 0 to +1. So these are 2 different magnetic resonance transitions that you typically see and can control. And if you look at this difference in energy as a function of magnetic field up to 1,000 Gauss, you have one that increases in frequency and one that decreases. And this is assuming that the magnetic field is parallel to this d-axis. All right, and I'll mention that a bit briefly too. But now we have, all right, so now we have the nitrogen vacancies that have your orbital degree of freedom within the band gap, and now you have a spin state that's sensitive to magnetic field, right? That's right, right. And since you have a 2 electron state, right, and it's an anisotropic system because you have a nitrogen and vacancy. So I don't think the wave function, it's also a triplet, so then they don't want to be in the same place. Okay? And if it was singlet, it would be useless spin-wise. So thank science for that. So now in our band gap, all right, we have, and I'm going to ignore the excited spin states for a second, but now within the band gap with this ground state, we have a splitting between the ms equals 0 and the ms equals plus or minus 1. And we can actually drive this with a microwave resonance. All right, at 0 field, it's 2.87 gigahertz. In field, it's higher. Now, if it's in the ms equals 0 state, you can excite it, and it will just come right back down. All right, and you get a photon out as you excite it. But if you drive that into the plus or minus state, what happens is that there's a certain probability that it's not going to just go up and come back down. It'll actually go through a different side channel, singlet state, all right, and emit fewer photons into your detector. All right, so in one case you have, let's say just full light intensity coming out if it's ms equals 0. And if it's ms equals plus or minus 1, there's a contrast, a lower amount of photons coming out in that case. And this actually is really nice from a quantum sensing perspective, because this dark state for the plus or minus 1 spin gives both a spin-dependent photoluminescence intensity, so the amount of light comes out depends on spin, but it also, this decay path will return it to ms equals 0. So it actually also gives you spin initialization. So if you're optically pumping these NVs, they just tend to go to ms equals 0, and you have nice state initialization. Now, what that kind of looks like magnetic resonance-wise is that here's a picture of magnetic field is about 0. You've got, and we're going to ignore a little bit of the details for a bit, but the 2.87 gigahertz is your optically detected magnetic resonance. This is the amount of photoluminescence as a function of microwave drive frequency. So as you hit that resonance, you see a dip in the photoluminescence intensity. And as you apply field, you can actually see that peak split into two different peaks due to the Zeeman interaction. All right, so now what have I effectively done? I can tell you what the magnetic field is, based on the amount of light coming out. Now, this is a pretty terrible measurement, but not very accurate, but it gets the point across, right? As you apply magnetic field, you get splitting, and then you can sense magnetic fields. Now, perhaps and this is an example of one of those, splitting in 0 field with much higher resolution. Now, here's another quantum number appears now, is that actually these peaks are not simple Lorentzians, right? You can see a triplet here. So who can guess what the triplet's from? You in the back. What's your name, sir? Oh, yeah, Justin, yeah? Oh, that's right. That's the hyperfine interaction. So this is actually, good job. I think you're going to be a great scientist one day. The hyperfine interaction shows up in these optically detected magnetic resonance spectrum because the nitrogen, the most abundant nitrogen that you actually get is nitrogen 14, which also has a spin 1. So this is a spin minus 1, 0, and 1 from the nitrogen 14. All right, and then you have the electron transitions on either side. All right, so this is actually a much better spectrum than I showed you before, less power broadening. We can actually see this on the microscope over there when we do our demonstration. All right, well, it's actually still a little bit more complicated too. All right, because not only do you have one orientation of NVs if you apply a biased magnetic field, so ideally you're applying a magnetic field along an axis of an NV, but you can actually have 4 different nitrogen vacancies if you have ensembles of them. So your biased magnetic field is going to be in a different orientation for each of these NVs, and at low field limit, actually this dipole-dipole interaction defines the quantization. So until you get past that, D is the predominant spin orientation, and then you'll get a different Zeeman splitting depending on which NVs you're looking at. So that, they experience a different B0.S term, right? And so if we look at a spectrum here, this is from Victor Acosta's thesis that I did not include as, I take a lot from Victor's thesis, it's very good. If you put it kind of at an arbitrary angle, you can actually see 4 different sets of 2 peaks, all right? So there's for the 4 different orientations, 1, 2, 3, 4, that's 0 to -1, and on this side it's 0 to +1. So you have 8 different main peaks, and then each of those have 3 subpeaks. But the nice thing about this is that actually gives you vector magnetometry in this case. So not only are you looking at the splitting of the outer peaks in this case, you can actually, if you know, and we kind of know the different orientations of this, you can actually reconstruct what the vector field is if you can do this magnetic resonance. Okay. All right. So that is the overview of the physics of the nitrogen vacancy. All right. All the quantum numbers that we have an orbital degree of freedom within this wideband gap. We have the electron degree of freedom, the nuclear degree of freedom, and then we have the fun solid state component that we have a defined crystal axis. Yes. Each of these 4? So that's because of the contrast of this screen, and I'll have to apologize. So this little guy here is green, is your nitrogen. This is a vacancy. This guy is a vacancy, and your nitrogen's there. And then this one is your vacancy, nitrogen there, vacancy there. So you have 4 different orientations of nitrogen relative to the vacancy within the diamond crystal lattice, right? Tetrahedron. So I'll change that to yellow next time. Nice high contrast. And so this is actually, the microscope that I have in the back over there, we can actually do this measurement live at room temperature with some of the diamonds I have. And we can play around with the magnet and actually align it to different crystal axes of the diamond. And here's a picture, though almost not necessary because it's right over there. But that's what we'll go look at it as another part of the demonstration. Now, the other thing about these nitrogen vacancies, this is the microscope that's controlling it. The diamond's actually down here. I've got a little eye-safe laser. Eye-safe laser, it's always good. Microwave amplifier, and this is actually my quantum controller that we use with the RF system on chip FPGA. So I'm going to talk a little bit about this because I'm quite proud of this one. It's an open source quantum hardware project that I adapted to actually work with these NVs and available publicly. So to actually control these quantum defects, so you actually have to have some pretty high timing resolution and detection. And so what we're actually using is really a new type of silicon within the last 5-10 years is a radio frequency system on chip, FPGA. So you can actually generate 10 gigahertz signals and detect them. And the nice thing is actually you can get these boards. This one specifically, academically, you can get for about $2,000. And it replaces a whole rack full of instruments. You can get more expensive versions too that have 8 input-output channels. But it's really the nice thing about this is like the power, the variability and the control. So you get nanosecond timing resolution for both measurement and microwave control in timing other instruments out of these relatively cheap boards. And there was a project out of Fermilab, part of these national quantum initiatives. They call it KIC, Quantum Instrument Control Kit. And it's actually made for superconducting qubits. And so it's all demodulated back, microwave signals coming out. And they have firmware for all these different boards running out of Python and Jupyter notebooks. All right. So but it actually didn't work for nitrogen vacancies because I needed photodiode readout at lower frequencies and photon counting, for example. So we made modifications to the firmware, worked with the team, actually Fermilab, and actually designed all the pulse sequences for quantum sensing. And I call it KIC-DOG. So it's Quantum Instrument Control Kit Defect Arbitrary Waveform Generator. All right. And so we made some cute doggy logo. So it adds laser control, low frequency readout, and all the different pulse sequences. And I'll have stickers for everyone later too. So if you want to check out the GitHub for this. This guy is over here. This is what we're actually using over there. This is the control board, and here's all the different quantum controls. So Rabi oscillations, Hahn echoes, and T1. And so this in some regard, this has kind of made it easy to do some quantum sensing with these solid state defects for some groups out there. Okay, so now I've talked about NVs from the fundamental physics perspective. This is our experimental setup we'll show later. Let's actually talk about actually how to make these NVs. So, how do you actually get nitrogen into diamond in a useful way versus for quantum sensing? And then the other part is, if you have NVs in diamond, how do you actually use it to sense something? All right. I mean, it's not just in free space. And as I mentioned, you have to get it close to your sample of interest, right, to actually do something useful. So first, let's just talk about making quantum defects. And so there's kind of, particularly for the nitrogen vacancy, which, as you know, consists of two things: a nitrogen and a vacancy. You have to be able to make both of those in diamond. And so the way you actually integrate nitrogen into a diamond is you can either do it during the growth phase, and the ideal way to do that is actually plasma-enhanced CVD growth. All right, and when you actually are doing that growth, you dope diamond on the order of 1 part per million with that nitrogen, and then you'll have nitrogen within the lattice. The other way to do it is actually with ion implantation, and this is slightly less ideal actually when doing super sensitive experiments, because that implantation can also cause damage. All right, and more damage than you want. You want to be able to controllably damage this. But we do this a lot too. And actually at Sandia we have capabilities to actually do this with nanobeams, because we have, well, not necessarily for nitrogen. We'll talk about that later. But we have a focused ion beam system that actually can, with custom sources, we can actually focus ions with 50 nanometer resolution into different materials. All right. Now, once you have something in the lattice, so while ion implantation, that actually creates enough damage that you can easily anneal and then get nitrogen vacancies. But if you grow it with CVD, you only have nitrogen in the lattice, and it's a bit too clean. So then you can actually use different damaging mechanisms to also create vacancies, even locally. So you can use pulse laser, and this is a fun thing we did using a 2-photon resist curing system that's at CENT. I used it instead to activate defects in silicon in that case, but diamond would work as well. So you get very high energy focused laser beam, and you can damage locally. You can do implantation either locally with something like a helium ion microscope or plasma fib, or do broad beam implantation of helium, for example. So you can hit it with helium. Helium's not going to stay in the diamond, but it'll leave damage. And you can actually do it with electron beams, as long as it's 150 keV or more, with TEM or e-beam lithography. Also fun thing we got is Sandia's Mesa recently got a fancy new e-beam tool that's 150 keV, more energy than the previous one, but it's perfect for actually making NVs in diamond. So it's just the threshold. And so we're going to take that tool and start locally making NVs with e-beam lithography resolution inside diamond. So left side is, the idea here is to integrate some element, or some ion, right? What's that? Well, we actually start, let me back up a little bit. Usually the ideal diamond that we start with doesn't have anything in it. So it's only carbon. So then you have to get the nitrogen or whatever other ion in there. All right. So that will give you the most control of the location. And typically we want nitrogen vacancies close to the surface of the diamond, so it can be closest to the sample of interest. Okay. And so and on this side then, so the CVD growth is usually only a few nanometers. All right. And so it's nanometers away from the surface. The ion implantation is usually low energy, so kilo-electron volts. So it's only at nanometers away from the surface. In some cases, we actually go up to microns if we want to do magnetic imaging, which is a lot of what I'll talk about. And then you can have a whole micron of NVs, but you don't want a 500 micron diamond full of NVs, because then your local resolution gets bad. All right. And perhaps I should have put this slide before this one, because this is our starting material. So typically we actually start with electronics grade diamond for these kinds of experiments. So this you can actually buy from a company, well, it's through Thor Labs now, but it's Element 6, subsidiary of De Beers, that sell the highest purity diamonds. It's like the only people that sell those. And a 2 by 2 millimeter plate, 500 microns thick, is almost $1,000 these days. Now this is the CVD grown version. So the traditional diamond that everyone probably knows about is those made by high pressure and high temperature, or long periods of time, right? And so we can actually get nitrogen-rich, high pressure, high temperature diamonds. I have some of these to show you guys too for the demo, but these actually come out with a yellow hue because of the defects in them. All right, and these actually have very few NVs in them. To make NVs, and we actually make a purple diamond, is that we take this yellow HPHT diamond, irradiate it with electrons, and anneal it, and then it turns purple because the emission spectrum is then more red, which is consistent with the NV. All right, so these are kind of the starting materials, but this is really the usual starting one. For example, here's our focused ion beam. We can focus this down to 50 nanometers, and you make defects and vacancies. Now that's not actually the end. You actually have to high pressure, or ultra high vacuum anneal these diamonds. So that migrates the vacancies to nitrogen, heals some damage, but you really have to watch out for any oxygen, is why it's ultra high vacuum, because diamond will just turn into carbon dioxide if you anneal it in air above 400. So you got to be a little careful with that one. And so we actually take it up to 1200 C. Now, one of I'll talk about this more later, is that diamond is actually metastable, right? It's made in high pressure, high temperature. So you can't damage it too much and still anneal out that damage, because it's more happy being more graphite-like in ambient conditions. And then we actually do surface treatment to control the charge state. So we typically oxygen terminate. Oxygen has a high electronegativity, so it pushes electrons back into the nitrogen vacancy, making it an NV minus. And we clean it with this triacid clean, which is perchloric, nitric, and sulfuric acid that's boiling. So that actually cleans the surface as well as possible. Thankfully, I don't do that. The students and postdocs do that, and it's probably best anyway. So after all this treatment, that's when you actually have functional nitrogen vacancies close to surface. I want to take a step back and talk about the focused ion beam capability. Now, I'll tell you why it's hard for nitrogen, but we can do it with a lot of other ions, which is important for quantum defects. So what we do is we make these fib tips. These are custom focused ion beam tips, which is a sharp needle point in a reservoir, and this total scale is a couple millimeters. And then you actually dip it into a liquid metal alloy. So gallium is the most traditional fib, because you can really melt it easily, apply a high electric field, and emit ions from this tip. All right, but at Sandia, we have a group that actually does this for a lot of different ions. This is the periodic table of things that we can do most easily in green and maybe in development in yellow. Now, nitrogen is hard because it likes organic things better than liquid metal alloys. So it's really hard to get into a liquid metal. We've shown a nitrogen beam before, but it's not that great. There's another group recently that has a plasma fib that can do it and actually implant nitrogen with 50 nanometer resolution. We actually focus mostly on the group 4s because those are also interesting defects for quantum information sciences: the silicon vacancy, germanium, tin, and lead. And actually down here, the length scale here is 5 microns. We actually implanted with our focused ion beam Sandia and SINT patterns with silicon vacancies and did photoluminescence to get these images, almost like a invisible ink that you have to have the right laser to see. All right, so I've talked about how getting how you can get nitrogen vacancies into diamond. Now we're actually going to move into actual quantum sensing. So I told you that it's earlier I mentioned that the most important thing is getting your nitrogen vacancy close to something. All right, and these are kind of the major ways that one does this. So scanning NVAFM is actually a really cool technique which gets you the highest magnetic resolution of any sensor that I know of. And what that is that you have this cantilever on a tuning fork AFM with a single NV on the tip. You're optically addressing this single NV, but you're moving things under it with nanometer precision. So you'll see changes in magnetic field based on the position of your sample under this, and that allows you to actually defeat the diffraction limit of light. So typically your magnetic sensitivity spatially, if you don't have such a instrument, is limited by the diffraction limit of your laser beam coming in. And for visible light and 100x objective, that's typically about 400 nanometers. All right. Now, if you don't really, if you're not going to be in this scanning mode, you can also do nanostructures and integrate your NV diamond onto materials. So one way is to make nanobeams You can pick and place them, and actually you can make diamond membranes, which are very thin diamonds, typically about 200 by 200 microns and maybe only a couple hundred nanometers thick. And you can place this on your material of interest and do your measurements. So there's you can improve collection efficiency, and then there's no issue with samples, but problem is you really have to move them around and put them on there. So then, as I had already mentioned, you can do resolvable implants where you implant in different regions. This allows you to do readout and measurement, and in this case maybe singles. This is actually an example of some photoluminescence that we did from our nano implantation, where these spots are a couple microns apart each. All right. Now, one of the easier ways where you kind of you give up on some of the high resolution and just you're settled with the diffraction limit, or you just collect light from a large area of a sample. This is actually a flake of HBN on a diamond, hexagonal boronitride. And there's a lot of NVs ensembles below this, and that gives you really fast coverage of your system, and then you get lower spatial resolution. So now you're limited to the micron scale. I'm mostly going to be talking about this kind of perspective, is putting your diamond that's full of NVs on something, or something on that diamond. Okay. But I wanted to take a moment to talk about the diamond membrane, because this is a fun technology that we were developing kind of at the same time as everybody else in the field. This is a smart cut technology, and this comes back to how diamond is metastable. So diamond doesn't like to be in the diamond form at ambient conditions. So what you can do is you can actually do a really high fluence implantation, and the stopping range of ion implantation in a material is kind of like a Gaussian at some depth. All right. So what happens is if you do a high fluence, you get this Gaussian-like region, some depth under the material proportional to the energy, and that turns into sp2-like carbon, which is more graphite-like. Okay. And you still have diamond on top of that. You can then anneal it and electrochemically etch that sp2 carbon away, and it releases this diamond membrane. And so here's an example of us doing it at Sandia. Here's a SEM image before, where you have darker contrast in this area, electrochemically etch it away, and you can see this, and you can lift out and put it on other places. Now, the reason that I'm not manufacturing this myself is because there's enough damage on that surface layer that actually the ideal way to do this is to smart cut and then do CVD overgrowth on top of that. And so we actually will do the smart cut part and then send out those diamonds to our collaborators for them to do overgrowth and make photonic devices on it. And the nice thing about that is that you can, silicon on insulator was one of the biggest achievements for silicon photonics, the ability to put thin silicon on top of insulator on top of more silicon. This effectively gives you diamond on insulator, so you can have diamond photonics integrated into materials. You can actually put this on SOI and then make diamond photonic devices out of it.
But you mentioned before about the interaction with photons. That's something that gets worse, better.
The surface interaction, or?
Interaction with photons.
So on these length scales, it doesn't matter, but you can actually phononically engineer some things too, and so you can make phononic cavities to enhance interaction or suppress it as well, and that's a field of study.
Okay, and phonons, do you also take into account chiral phonons?
What kind?
Chiral phonons.
Not unless it's a specific science experiment towards that direction. But for these simple, for the phonon sideband of NVs or other defects, it's just the phonon.
The phonon really no frequency, right? Really cannot hear anything. The phonon is sound is really no frequency.
I have to think. I think it was like 50 MeV was the level, right? But we can't see. You can't see sound with your sensing, as far as I know. Though you can use it to actually manipulate the spins, phonons, in some cases. So people use that for silicon vacancies in diamond, for other reasons. All right, so now I've talked about making NVs in diamond and actually forming your diamond to make a decent sensor. I'm going to now move on to talk about some actual measurement with NVs in diamond. So more specifically, in practice, how one does sensing with NVs. And I'm going to talk about DC magnetic fields first. This was an area that really we started in because we had a really good postdoc with Peter Polykahias, who really brought this to Sandia about the same time I was starting. And he and I paired up and cranked out a lot of nice nitrogen vacancy magnetic imaging studies. So I want to give you the scale too of where the NV sensing sits relative to other quantum sensors. And pardon me if I've offended anyone on sensitivities, but this is approximately it qualitatively, particularly for spatial resolution versus the magnetic noise floor. So how sensitive you are. Better sensitivity means lower magnetic field noise, and then spatial resolution goes down in this. And so, vapor cells have an extremely high or extremely good sensitivity, but their spatial resolution isn't so high, right? So you're very susceptible to magnetic fields, but you can't accurately pick them out. Squid magnetometry, and this is mostly for at room temperature. And for example, scanning magnetic tunnel junctions, you're starting to go lower in spatial resolution, but also higher in your magnetic noise floor. And so NV centers, sit about here. So you can get actually, and this is from a imaging mode. This does not include scanning, which goes a couple orders of magnitude lower even. And so you actually get, you sacrifice your sensitivity to gain high spatial resolution. Now this is kind of DC sensing. The AC sensing, where this is actually more the kind of coherent effects with T2 type noise. And then you can also look at broadband through T1 type noise. And we'll talk a little bit more about that. But the point is you're also beating out, and this is for more condensed matter type systems, ESR, MUSR, NMR live up here. Here you're getting down to lower length scales again with good sensitivity. Okay. Now a little refresher about sensing magnetic fields. This is the vector magnetic imaging case, and as you increase magnetic field, you see these splittings change. A typical experimental configuration, aside from the one we're doing there, and this is actually magnetic imaging specifically I'm talking about. So what we're doing in an imaging case is we have a microscope. This is built inside a Helmholtz coil to apply a small bias magnetic field. And inside there, we actually have, this is a horrific clip art of an objective that I made, where we pump it with green light and detect the red light, but we actually project it onto a camera. All right, so instead of just projecting it onto a photodiode or a single photon detector, we have so many NVs in this diamond, about 4 microns of NVs at 50 ppm along the surface. We can actually see that red photoluminescence and sensitive enough for a camera to read out. And so this gives you spatial resolution down to the diffraction limit, so 400 nanometers. The field of view of this can be hundreds of microns to millimeters, and the sensitivity then is microtesla per root hertz per pixel. So, many orders of magnitude less sensitive than other quantum sensors, but really giving you this spatial resolution to look at interesting things at these length scales, and we'll talk about that here shortly. So how this works is that, again, we're taking these spectra. This is, I'm going to ignore some of the extra peaks and just look at, we'll just consider the ones where the NV is along the magnetic field axis. You find this magnetic splitting between these peaks, and you can calculate what the field is by multiplying that splitting by, the frequency is proportional to 5.6 megahertz per Gauss. And what we do is we take this spectrum, we take pictures as a function of frequency drive. So each picture actually will have a spectrum in it. And then you can take all these pictures and all these spectra, fit them for the magnetic field, and you can get a magnetic map. Now in this case, this sample was microbar magnets that we intentionally fabricated to qualify our quantum sensor. So you can actually see kind of the dipolar shape of a magnetic field from these nanomagnets. Now, while this is a contrived, experiment, we moved on to actually use this to look at electronic devices. So the system we wanted to initially demonstrate magnetic sensing in, and particularly for detecting currents in electronics, was this 555 timer electronic. And the nice thing about this was that it had the right feature length scale that was perfect for this 400 nanometer resolution. All right. And so this is the device. I think it's about 2 millimeters across. And what happens with this device, if you put the right electronics on it, it turns on and off at some periodicity. And it's sufficiently complex, we can also simulate this with SPICE and COMSOL. And so this is actually a COMSOL model of showing where the current goes through the device, depending on the state. And so what we're doing with this is just showing initially that we can detect currents through devices. A current, as you probably know, will create a magnetic field, a flowing current. Due to the right-hand rule in Maxwell's equations, you can pretty much show what that is. So this is an actual magnetic image from that NV magnetometry where we put a diamond on top of the device. And this is the output on state. In the simulation, you can see the current going through the device, which follows this large channel here. All right, and this was actually the COMSOL simulation as well. And we also saw exactly, pretty much the same correct behavior going through when the device was off, dumping all that current into ground. And similarly, represented here in the simulation. In this case, we actually even put the diamond on top of the wire bonds for the device. So it's standing off by about 50 microns, which actually blurred the resolution a bit. But the point comes across. Now, this is just the magnetic fields. You can actually invert the Biot-Savart law on this and actually show where the current density is and the direction of it. So this is the current density. We don't have a vector magnet here, but it shows where it goes. And this is the actual COMSOL simulation. This case, it doesn't blur because this is the actual what happens. And there's no reason for the current to blur. So you can actually show where the current is running through these devices. Now, that was a proof of principle, and we actually incidentally had a device that failed. So to be able to access this, we had to decap the integrated circuit to be able to put our diamond on it to get good standoff. Now, one of the devices actually did not behave as expected. Now, we didn't end up publishing this, but it was a fun exercise. One of them was actually working, so it had this periodicity. And under the same bias conditions, the broken one had a much sharper peaks with longer period. Now, if you look at the magnetic image, and I'm zoomed in here, you can see a specific area that is behaving different on this device. So here you have the current flowing here, which corresponds to this line. And in this case, you actually have much less current going through that path and a little bit extra through this channel right here. And so these measurements were performed by Polly. I actually taught myself COMSOL to do the simulation. And what I found is that if I tweaked the conductance of this transistor here, right, that would actually be consistent with this failure mode in this device. And we also found that some resistors values were a little bit off in this device, almost like the doping was incorrect. So, this is actually now kind of a real-world application of these quantum sensings where we can actually, diagnose electronic failures using these diamonds. And so we've done a couple other experiments in this regard. One was from a group that does delta doping of phosphorus and silicon. We had these hall bars, and we could actually see broken paths on this hall bar from fabrication mistakes. All right, so this was like a break in that, and so the current would actually go around this way and jog here. That actually can't, you're actually seeing the current in real space. And I think more interesting, most recently, is the Sandia fabricates ion trap qubit devices, which is this bow tie. Now, these are supposed to have a lot of electrostatic gates on them. All right, so they're not supposed to have any current. But they were finding failures in their devices where they actually were drawing current where these electrostatic gates, from a bulk probe test, like a multimeter. So they asked us, can we find where this actually happened? And what Pauly did was he took his diamond, and you can see where we moved it across. You can see the current actually going through from this magnetic field map, all right? And then it stops suddenly here. All across the board, having measured like 6 to 10 different failures, They always failed at a specific point, which was a trench capacitor in the device, so we decided to remove that. And we know that it was pretty confidently there too, because we also intentionally blew up several of them to make failures elsewhere. And it was not consistent with the current paths that we saw. So we are trying to suss out whether it was ESD, for example, otherwise. Okay, so that's kind of applied physics direction. I want to point out some stuff from the community and also directions we're going with some DC sensing. One of them, which is a lot of fun, is in a diamond anvil cell. So if you want to do physics at ultra high pressures, you actually use diamond anvil cells. And it's challenging to get electronics. This area typically is around 50 microns, where you have some sample and electronic leads. It's not easy to do magnetometry at high pressure. But in the last 5 years, people have been pushing towards integrating nitrogen vacancies on the surface of one of these diamond culettes. You press it down, and you're right next to the sample now. And now at high pressures, up to hundreds of gigapascals, you can actually measure magnetic fields. So this is from Norman Yau's group, and they're actually looking at some of the hydride superconductors, which have extremely high superconducting transition temperatures, and they see variations in the magnetic field. They can map out the Meissner effect in these materials, right? And so this is just an emergence area where we're, and recently we're demonstrating sensing at high pressures too, and starting to integrate with materials. Another area of condensed matter physics, and again, this is temperature. So this is actually low temperature, 10 Kelvin. Twisted 2D materials that are magnetic, such as chromium iodine, is an interesting material for condensed matter physics. You can actually see magnetic domains in this as you cool through the Curie temperature. Okay, and so this is from the wide field imaging perspective too. We still haven't, I'm not going to talk about the scanning NV probe, but you could even do this with scanning NV and get higher resolution, for example. Is another area people condensed matter physics. Okay. So I'm going to talk about AC magnetic fields now. A lot of the stuff that I was talking about was static fields, either from like a constant current, or in the case of condensed matter physics, I showed examples of Meissner effect or magnetic domains in ferromagnets. AC magnetic fields is another area that of sensing possibility. A recent one that we did, similar to the wide field magnetic imaging, from DC perspective, we can also do AC imaging. And this is actually what we're calling differential Rabi driving. So if you apply a short microwave pulse, you can change your spin from the 0 state into the XY plane on the Bloch sphere. And depending on that microwave intensity, you rotate around here. And that's what this picture is here. This is the this photoluminescence intensity, which projects onto the spin state. This is the spin state going from 0 to 1, and then that's a T2 star type decay. Now, we do this with a microwave loop with a diamond on it, but then you can also have some device under test also have a very small AC field on it. All right, so this is like up to 4 orders of magnitude smaller at the same frequency, and you can see how much that shifts your Rabi drive. All right, so in this case, the red was just our microwave loop, and the green is with some device. In this case, it was just a wire as proof of principle. And so you can actually get 4 orders of magnitude weaker than your microwave drive going through the sample to actually see these slight changes, and actually map that out just like we did with the DC field. So we can still project that onto a camera. This is actually a simple device. This is the microscope that we built when we use permanent magnets here to get higher magnetic fields. I think Peter was mentioning something like this, that you can shift the resonance that you're looking at and coupling into these AC fields by shifting the Zeeman effect. This allows us to go from 2.87 gigahertz down in frequency, down to hundreds of megahertz, tens of megahertz, with the 0 to -1 transition, or actually up for the 0 to +1 transition from 2.87 gigahertz to whichever frequency we can actually drive. So this is kind of comes into that dynamic range of NVs too, right? So you can go from DC sensing, and then you can go from megahertz to gigahertz. That is the higher end of the range. I've got an example from the intermediate scale too. But nonetheless, we did this experiment, and we can actually show, in a wire, the AC magnetic field that gets mapped out, which perfectly matches what we expect. So now we're going to start applying this kind of AC imaging to other type devices where instead of looking for failures in the DC realm, you're actually looking in the AC realm. And that can give you access to failures like open circuits rather than short circuits, where you end up having like a little antenna that's sending out signals. Okay, so this was kind of this high frequency scale. I'm going to take a step back to slightly more complicated measurements, which are intermediate frequency scale, where you're actually doing Hahn echoes in CPMG. So people that may not be familiar with the Hahn echo or CPMG, the Hahn echo is the simpler version of this, where you start with the spin state. You perform what's called a pi over 2 pulse here in the XY plane. Your spins will process in this XY plane, but they actually end up decohering because of variations in the local magnetic field. That's a T2 star like. This is inhomogeneous broadening, is what it's called. But then if you actually apply a pi pulse, the spins coalesce back together in their initial position at a time tau of delay. And I'll show you a nice animation of this. In the case of NVs, we actually have to project it back onto the 0-1 axis to read it out, because we're reading it out optically. But this is a very standard technique within NMR and ESR. Now we can actually see a Hahn echo. I don't know if anyone else has seen this, but if you look up Hahn echo on Wikipedia, they have an amazing animation. So there you tip. Now you have inhomogeneous broadening, different Larmor precessions. You flip it, and then they coalesce again and give you an echo. All right, and they coalesce at this tau. That gives you this signal in this HC type sensing. Now we can actually use this to sense sources of decoherence. All right. So in the perfect case here, you get perfect coalescing of those spins, right? But if you had some noise source, and I'll show you here, a noise source that is periodic within this 2 tau value between pulses, you actually end up locking into that signal. Now, often people in the qubit community will use this, it's called dynamic decoupling, to actually decouple from noise. All right, you want to get away from these specific noise sources. With sensing, we actually use that to detect nuclear spins. So in this case, this is the intensity of the Hahn echo, or a CPMG sequence, as a function of this tau precession time. You get a standard T2 decay, but then you get an extra decoherence here. In this case, this was actually specific to the nitrogen spin. All right, so this is we were sensing just the nitrogen within the material. Now that's for, nitrogen's already there. What if you want to look at something else? So in this case, we actually used HBN, which has boron in it, and we wanted to try nanoscale nuclear magnetic resonance. So by doing this dynamic decoupling sequence and tuning our tau, we can lock into different frequencies. And what we have here is actually the spectrum, the nuclear quadrupole resonance spectrum of a few layers of hexagonal boron nitride. So now we're actually doing magnetic spectroscopy at the nanoscale. Our group particularly did it with ensembles of NV about 10 nanometers from the surface, where we actually get much better signal to noise over if we expand our beam and interrogate microns at a time versus singles, which people had previously done. So you only get a single NV sensitivity there. So you can expand sensitivity by looking at multiple NVs rather than few. All right, so let's see what time it is. All right, I'm going to skip over T1 relaxometry pretty quick. This is kind of a T2 type effect where you have spin dephasing in the XY plane. There's also, if you want to investigate spin noise, particularly of materials, you can look at a T1 relaxation process where you completely invert the spins and you wait for some magnetic source to relax you back to the initial state. And that's called T1 relaxometry. There's a nice result recently from a friend of mine that was looking at superconductors on diamond. And you can actually see an enhancement of critical fluctuations through a phase change right at the superconducting transition temperature. And this was with BISCO on diamond, which is one of the high temperature superconductors. All right, and you can actually map out the phase diagram. You can actually say something about the pairing symmetry of your superconducting electrons by looking at the temperature dependence of this T1 value below TC2. And there's theory that backs this out, but this is coming from a fundamental science perspective of quantum sensing. Okay, so I want to mention one more defect that we're looking at, which is gives an interesting alternative to diamond. I've told you how it's hard to integrate diamond with other materials. You have to really modify the diamond or find the right target. Hexagonal boronitride, while you can't you can't get the boron and nitrogen to be isotopically completely enriched out, there are a couple tricks you can play. But this boron vacancy is actually quite similar to the NV, as it has a spin 1 state, and you can do optically detected magnetic resonance. All right, so what we actually did, we had an experiment where we were trying to do spin polarization experiments, but this is a HBN flake with boron vacancies. We make those just by helium bombardment. So in that case, you're just looking to knock out the borons, right? You don't have to dope it, you're just doing damage. And you can actually do a magnetic ODMR type spectrum. This one, doesn't look that great. A lot of it is because of all the nuclear spins around. So we actually, even though we can't exactly isotopically enrich them out, we converted, we got a sample that has, remember which isotopes exactly, boron 11 and nitrogen 15. And since the nearest neighbors to this boron vacancy are 3 nitrogen spin 1/2, that gives you the total spin 3/2 states, and you can see 4 peaks from the neighboring nuclear spin states here. But this is sufficiently more narrow that we can actually look at DC type sensing, or similarly do T1 and T2 type sensing with this material. And now you have the power of exfoliation, where you can put these 2D sheets of hexagonal boron nitride with boron vacancies onto other things, like other materials of interest. Okay, so we have talked about nitrogen vacancies in great detail. In conclusion here, what I've shown you is actually these nitrogen vacancies, or even some regard boron vacancies in HBN, have a wide range of sensing modalities, length scales of sensing, and frequency scales, all for this quantum sensing across applied physics and even fundamental physics. Thank you.
Thank you very much, Andy. Do we have any questions for Andy?
Thank you. Hold on for the mic.
Thank you, Justin.